All right, so speed. Draw speed. Okay. Potential energy. So what do we got for potential energy?
Stored energy that is not used.
Stored energy is fine. I think I heard to do work. I like that. Examples?
Water behind a dam.
Okay.
Gas in the tank of a pump.
Battery. Rock on the hill.
Battery.
Oh, a bow being
Car,
drawn.
hill.
It's like a bow.
Like being drawn.
Like a bow. Like a little, yeah. Like a- Or I heard like
It's
a
actually
bow
the
being
biggest one of the
drawn.
potential.
And I thought it was like a poison.
Okay. Kinetic.
Energy and use.
Object movement.
The water flowing through and yeah.
Kinetic.
Sure.
A falling rock.
I think we have that one already. What else do you want?
Airplane.
Excuse me?
Airplane.
An airplane? Sounds like a falling rock. Airplane.
Same thing, right?
Flying? Speaking of airplanes, horrible,
Yeah.
right?
What happened?
Iran thought we were invading them and shot down a plane that had left their own airport.
Yikes.
Oh yeah, I heard about that. It was a
So-
Boeing 737.
So those people's deaths are on Trump's head for starting this whole thing.
Yeah, that's right.
But, I mean, he doesn't take responsibility for anything.
Missiles at military bases, but it actually hurt anyone. Nothing's taken perfectly to anyone.
So the significance of this Fahrenheit scale being zero?
Water can still freeze with salt in it at 0 Fahrenheit, I believe.
Can't.
Can?
Or
It's the
can't,
thing.
can, or can't melt.
It can freeze at 0, but at
Sure.
32 degrees it cannot.
No
Ice does not
melting
is salt.
of 0 degree Fahrenheit, that degree on the wrong side.
Is that true for all salts? Just 'cause I don't know if it's different. Is that true for all salts?
Yeah, it doesn't, this is based on the water, not on the salt. So once water hits 0 degrees Fahrenheit, it doesn't matter what you put in it, it won't liquefy.
Oh. And so what's the negative 32?
Nothing.
I thought
You mean 32?
Is it 32 degrees Fahrenheit? I thought it was negative 32.
That's more degrees.
No. Freezing is 32 degrees Fahrenheit,
Okay.
right? Not negative.
0
32.
is where you can't use salt to melt ice.
You had it right the first time. Negative 32 degrees Fahrenheit is just freaking cold, right?
Try to for 63.
That would be Upper Peninsula in Michigan, Canada, Alaska.
Minnesota last year, February 3rd.
Really?
Yep.
That's cold.
It was very cold.
Okay, a moving car has specific amount of kinetic energy. If it were to crash into a tree, where'd the kinetic energy go?
The air through the sound of the tree.
Okay, so there's a lot of, sound is produced from air movement. So remember what energy is.
Heat.
It can be. Okay, so we could throw that on there. Some heat was produced, sure. Not a ton, but what else we got?
I said transfer, like a transfer of energy
Okay,
from the car into the tree.
how so?
Well,
So let's back up for a second. Energy is, what's its definition? Potential to do work. We already have the heat part. What work was done?
broken the tree or breaking the tree.
Okay, so
Either that or metal crumbling.
broken
Yeah.
branches, which is maybe a trunk. Definitely like broken car, right?
driver.
It takes a lot of energy to bend metal. It takes energy to break glass. It takes energy to,
Coming outside the car.
yeah, to move, move the tree a little bit. All of those things take a significant amount of energy. So all that energy was used to move stuff and produce heat and make the air move. So you got that sound and whatnot. So the energy's still there. It's just now in a different way, different place. Check whether, what was the temp?
41.
41 degrees Fahrenheit. So what do I do with this 41 degrees Fahrenheit?
Convert it to Celsius.
I know. That's what how to do that.
So 41 minus 32 times 5/9.
Anything else?
Parentheses.
Parentheses.
To get it right.
Parentheses. If you don't have those parentheses, what's going to happen?
32 times 5/9 minus, or.
Yeah.
Yeah, plus 41.
PEMDAS.
No, minus
Minus.
out of the,
We'll have-
minus that from 41.
Yeah.
So can't have that. Don't want that. What I need to do is subtract off the 32 off of the Fahrenheit number. Then I multiply 5 by 9. So 5 and then divide by 9. I would, well, what's this value work out to be? Anybody?
A little over half.
No, because you have the minus 32 on there as well.
Oh, I thought you were talking about just 12.
Based off of what we talked about last quarter, what temp Celsius would you expect this to be? 5-ish?
Is that right?
What temps do you know in Celsius? You should know at least 4. 0 is freezing, 100 is boiling, what else? 37 is body temperature, and room temp was what? Celsius.
Celsius, not. Let's just think it's just.
20. 20-ish, somewhere in the 20, low 20s, high teens is regular room temperature. So what's this temp? Before you even do the calculation, 41 Fahrenheit should be what? Cold, right? It's not, 41 Fahrenheit is not far from 32 Fahrenheit, which is 0 Celsius, and it's significantly less than 20 or room temperature, which would be like 70 something or other. So this needs to be a small number, and what do we get? 4?
5.
5?
41 minus 32, 9. 9 times 5 is whatever, and then divided by 9, 5.
Yeah, it's 5 degrees Celsius, right? Because that works out to be 9, so they cancel out, and you're just left with 5C. All right, so this should really be 5.0 degrees Celsius, because there's 2 sig figs in 41. So 2,500 calories, and then for every 1 calorie, it's 4.183 joules. So I don't know what that is, 10,000 something. .18. No, it's 4, isn't it?
Yeah, so
It's not 3, it's 4. My bad.
What?
Isn't that a 4 right there?
10,000.
but, no, it's not a calculator. And because sick pay.
10,000.
It's just 2,500 times 4 with some change.
I messed up on factoring in the keys.
So this should be 10,000. Or 1.0 times 10 to the 4th joules. Because there's 2 sig figs, just those 2. Alrighty, so I want to calculate the amount of heat needed to raise the temperature of 250 grams of water from 2 to 98. So 96 degree temperature change. I'm looking for the amount of heat. So I'm going to start off with 1 calorie per gram degrees C, because then that gets me the unit calories in the numerator where I want it, because my answer needs to be calories or joules. So it's 250 grams, so I'll put 250 grams up top, that way the gram value cancels out. And then what am I going to do with the degree C?
It's going up.
I definitely have to, it has to be on top so I can cancel out the degree C in the denominator. And what's the value? Everybody okay with 96? It's the change in temperature, not the temperature. So then I've got 250, clear, 250 times 96. So 24 calories. Looks like I have 1 sig fig. That's not well done, but okay. Oops. So 20,000 calories.
If that was a 25,000 would be 3,000 or
Yeah.
round up.
It'd be 30,000 or 30,000, yeah. If you add 350 calories of energy to 1.25 kilograms of copper, if the Nielsen temperature is 19, what's the final temperature of the copper? All right, so the easiest way to do this one is we're trying to find a temperature here. So I'm going to put, what are we doing? Copper? What is it? Is it 0.098?
0.092.
92. Yeah, that's right. 92. Okay, so it's 0.092 calories, grams, degrees C. So why did I write it upside down this time?
Because you're looking for calories, or degrees Celsius, sorry.
Yeah, I'm looking for a temperature, so I put the temperature unit in the numerator. I need to get rid of the calories and the grams. So the calorie one's easy. There's 350 calories here, so that'll cancel out with the denominator. And the grams one is almost as easy. I'm just going to write 1,200 grams, since that's the K means 1,000, right? So 1,000 times 1.2 is 1,200. And so then the grams cancel. And then I get this degree C number, which is 350 divided by 0.092 divided by 1,200. So this says 3.17 degrees C. Okay, am I done?
No, you have to add 19 degrees Celsius to 357.
Looks like 2 sig figs, so 21 degrees Celsius is my answer. 22 degrees Celsius, 22 degrees Celsius. So that's the change in the temperature. That's the amount that the temperature changed after I added this 350 calories. So I was already at 19 degrees Celsius, so then I just need to increase that temperature that I was at another 3 degrees. How come it was such a small temperature change?
Because it's not hard to change the
It's not hard to change the temperature of copper. Well, up here, it was, 20,000 calories, 24,000 calories, as opposed to just 350 calories. So copper is a lot easier to change the temperature of. Is that it?
No, it's that one.
I thought there was another one before this one. So this was the fun one, right?
Driving me nuts.
There's a couple of things that you need to recognize. So anybody want to start us off with the things that we need to understand when we're looking at this problem?
We need to start out with finding the change of temperature in the water, because we're given alternatives for that. Or, yeah, sorry, we need to do the equation of like 1.0 calories over grams times Celsius.
Okay, but what do we need to understand about the problem before we just like jump into doing calculations, which is usually what people do. They just jump in and start doing calculations and be like, all right, what am I going to do with these numbers? Okay, so first and foremost, you put the lead into the water. The lead cooled down, and the water did what? The water heated up. Okay, so understanding that, it's obvious, but people forget about that stuff, and that came back to bite probably half of you in the ass when you were doing the math at the end for this. Made you do something you didn't expect to have to do. Okay, so then what else? So the lead goes down, water goes up. What else?
They'll reach an equilibrium.
The final temperature of the lead and the final temperature of the water are the same number. That is incredibly important to understand. And then what else? Along with the temp change thing. The lead had a certain amount of energy inside of it, right? What happened to that energy?
It went into the water.
So tell me what happened to the lead's energy.
Decreased.
So how do you mathematically assign a decrease? The lead's heat is negative.
It's not much.
You don't have to multiply by -1. It is inherently negative. That is what its value is, because it lost that heat. And so there's one more thing you need to understand. That heat that we're talking about with the lead What else? What else about that? The lead lost a certain amount of heat. Let's just say, for sake, it was negative 500 calories. So tell me about the water. It gained 500 calories in that example. So whatever the water's Q is, it's the same numerical value, opposite sign of the lead's value. Those are all the things you need to think about before you even start to do the math. Yeah.
I just realized, when you get the amount, that final, wait, no, that is the final, so you wouldn't have to add that to the 60. So I just answered my own question, sorry.
I don't know what you're asking me, so good. All right, so we do have enough information to calculate what thing right off the bat?
Calories that went into the water.
The calories that the water absorbed. Okay, so 1 calorie gram degree C. The water is 300 grams. And the temperature change is 45? 45 degrees C. So the C's cancel, the G's cancel. And I get some number here. Calories. So that's the amount of energy that the water gained. Great. That number is going to tell us what?
20 calories went, or got lost by.
So it starts out negative. Why? Because it lost that energy. So there's no need to like back end this with a -1 value. It is negative. All right, so great. We can use the equation for this. You can use Q equals MC temperature final minus temperature initial. I mean, that's fine. Or you could think about it. Or if we do it this way, then I know this value because I just figured it out. I know this value because it goes in right there. I'm going to look up the specific heat. I forget what it was. I'm going to give it. Oh, okay. So I look it up right here in the question, and then I know one other piece of information. I know that this temperature final is 60 degrees Celsius. So I know everything that I need except for that initial. So you could do algebra and solve it and get TI like that. I always use the railroad track method and think about the problem. So what are we looking for in the problem? I'm looking for temperature. So then I'd go ahead and start with degree C calories, and this value is 0.038. So it's upside down because I'm looking for a temperature. And then I know that my calorie number is negative 13,500 calories. So the calorie gets canceled out. And I know I've got 80 grams. So then the grams cancel out. And then this gives me 1350 divided by 80 divided by 0.038. This gives me 44. Let's go with that.
Last vapor rate is at 1,760 degrees Celsius. I was like, wow. I don't understand why it was so high.
It doesn't tell you what state that the lead was in.
Well, it says a chunk. So it does,
Chunk of air.
You're right, but
It's painful.
Is that 4,440?
4441 degrees C. Okay, so what value is this?
That's T.
That's the change in temperature, right? So this is my delta T. So then my equation for delta T is temperature final minus temperature initial. So I know my final temperature is negative 4441 degrees C. I know my final temperature is 60 degrees C, and I know my initial temperature is what I'm looking for. So you just rearrange this, throw it over to the other side. So this ends up being temperature initial is equal to 60 degrees C plus 4441 degrees C. So, I mean, you also knew it had to be a plus there because the lead was hot. And if you brought the negative sign over, then you're saying that the lead was frozen and then heated up the water. So that doesn't make any sense. So the initial temperature of lead was No,
4501.
4501. Yeah, that makes sense. Degrees C. I only have 2 sig figs or 3. 3. So 4.5 times 10 to the third degrees C. So super hot. Why did it have to be so hot? Hard to heat water. Okay, great. So it's difficult to heat water. There was more water than there was lead. And so this problem, I think, really shows you the ability of a substance to hold heat. So how much heat can lead hold? Not much, right? I had to get the lead to over 4,000 degrees to heat water up how much?
45.
45 degrees. I mean, it went from cool water to warm water,
That
right?
temperature of the lead, like way over its threshold
Well,
to
that's what I said.
be liquid.
Doesn't matter. Can I get lead to be that temperature? I'm positive there is lead in the universe at that temperature right now. 100% sure. Doesn't really matter. It's just a problem. So I also didn't tell you anything about the atmospheric pressure, so it could still actually be a solid if the atmospheric pressure was like 4,000 atmospheres. So this is by far as complicated as you could possibly get with a specific heat problem. There isn't anything crazier. You're actually going to do this in lab today. Kinda. You're going to take hot metal and put it into water and see how much the water temperature goes up and then gauge that against.
You gotta find out how.
Nickel or iron or I'm not giving you lithium or potassium or
Sounds like so much fun.
francium or anything like that.
How about your angry?
I can even get a hold of that.
You couldn't. You can't buy any of it. The only way to get a hold of it is to make some.
Which is stupid.
Not actually make it. Just wait for it to be made and grab it before it decays, kind of thing. Okay.